Hi all, this is Mr. Yeager for chemistry, and we are starting our new unit on chemical reactions. Okay, so we now have, hopefully understand naming chemical compounds, all the different types, acids, covalent, and ionic. And now that we have that down and understand how they come together, we can start mixing them up and actually have them react and form new products. So that's what we're starting with. Again, as always, this presentation was made by another amazing chemistry teacher in the content group I'm working with, and here we go. All right, so kind of taking you back, hopefully some prior knowledge here. Back in physical science, you learned about physical versus chemical changes, okay? A physical change is where you are changing some appearance of that object, of that chemical, but you're not changing what it is in terms of its atomic level, okay? It is still the exact same chemical, okay? So you're changing what it may look like. You might be smashing it, like it says there, crushing it, but it is still the same substance. The hardest one here that people struggle with on physical changes is when you melt, boil, or dissolve something. It is still present. It is still the same substance. So I always use water as the example. If you have water and it freezes, it's still water. We just call it ice. Ice is water. So you're just changing its appearance from a liquid form to a solid form, but it is still water. And same thing goes with boiling, where you're changing it into steam. Steam is still water. It's just in gaseous form. When you're dissolving something, when you put salt in water, the salt is still present in the water. You might not see it anymore because the ions have split up and are surrounded by water molecules. We'll get more into that when we get to our solution unit. But the salt is still present. It has not chemically reacted with the water. That's the other part. A physical change does not have a chemical reaction. A chemical change is a chemical reaction. So chemical change and chemical reactions are the exact same thing. You are changing the atomic level of how those substances are arranged at the atomic level. All right. Now, some verbs that we can use that show chemical change is when you burn something. When there is fire involved, you are definitely creating a chemical change. Now, if you just are using fire to heat something up over the fire, that's not a chemical change. That would be a physical change occurring with the temperature change of that substance you're holding above the fire. But the object that physically is burning, that is undergoing a chemical change. It won't burn forever because it's changing into something that doesn't burn as easily. When you cook, when you react, when you rot, bake, all those different examples would be words we would use for chemical changes. So we are definitely much more interested in the second one in this unit, the chemical change. We're going to be interested in what are the signs of a chemical change, and then how do we obviously write it out with chemical formulas. Okay, so signs of a chemical change, you can see the list here. Probably the biggest one is there's a change in temperature. And I understand that might not always be completely apparent if you do a chemical reaction, but there will be a change in temperature during any chemical reaction because you're breaking and reforming bonds, which requires an energy change. We do have something called formation of a precipitate. Get used to this word, precipitate. A precipitate is a solid that will form when you mix two chemicals together and all of a sudden something solid comes out of it. So you usually have two liquids and then a solid is produced from those two liquids. A change in color that occurs that doesn't involve you adding any dyes or paint or anything like that. So the objects change color and, again, it's just automatic. It's something that will be instantaneous. Well, I don't want to say that. Actually, it might not always be instantaneous, but a lot of times it's instantaneous. Production of a gas. So there's bubbles that form, but it's not boiling. Odor change. I mean, we could add in taste change. You know that if you've eaten something that you're like, oh, this isn't right. Okay, that's because that food is changing into another form. So I know there's sometimes some struggles with this because you might be going, I cook chicken. I have a raw piece of chicken and then a cooked piece of chicken. I still call both pieces chicken, but they are chemically different because you have rearranged their proteins and the chemicals in terms of how the atoms are arranged when you cook it. Okay, and that's why it tastes different. Don't eat raw chicken. All right. So, in a chemical reaction, we have two parts. We have reactants. Exactly as they sound, they are the things that react. They are the beginning products. Don't want to say products, sorry. They are the beginning substances. All right? Products is what's created. So, it'll be reactants forming products. All right? And then you have your nice little diagram here. You do need to make sure you recognize all the different parts of this. We do ask about each of these in questions on quizzes and tests. All right? The reactants are always written on the left-hand side. Okay? The left-hand side of what? We have something called a reaction arrow that goes in between it. So we're going to write the reactants, the chemicals that we're putting together or that are going to react, on the left side of the arrow, always. And then the products are always on the right side of the reaction arrow. We will be including subscripts, which you already know from chemical compounds. Okay? So subscripts are the small numbers. We will be introducing the use of coefficients. Coefficients tell you how many of that compound that you have, and you put that in front of the letter. So, while magnesium is a single atom, I'm saying there will be 2 magnesium atoms. This is different from O2, where there's 2 O's chemically bonded to each other already. Okay? So we have coefficients, you have subscripts, and you have reaction arrows, products. We're not going to get too much into this. I'm glad it's being stated. You might see a letter in parentheses after the compound, and that's the physical state it's in. So S for solid, G for gas, L for liquid, and then we're going to have something called AQ for aqueous, which means it's in solution. Okay? Now, the reason we write chemical reactions or chemical equations is what we're going to say, is due to the law of conservation of mass. This is why we balance. So if there's a question saying, why do you balance a chemical reaction? It's due to the law of conservation of mass. Sometimes this is written as conservation of matter. It's the same thing. But what we say is you cannot create or destroy any mass. So if you have 1 atom of magnesium on the left side, but 3 atoms on the product side, that does not make sense. You can't just create 2 more atoms. It must mean there must be 3 atoms of magnesium at the beginning and 3 atoms of magnesium at the end. They just have rearranged where they might be. Okay? So, chemical equation is what we call the written out chemical reaction. So what you saw on the prior page, this is a chemical reaction. This is a chemical equation. Okay? Again, when we balance, we're saying that we're getting the same number of each type of atom on both sides of the equation. All right? And we will have different chemical formulas on both sides. Okay? If you see the same chemical formula on the reactants and product side, we actually subtract that from them. We cancel each one out. Okay? Coefficients. I mentioned those. They are the numbers in front of the chemical similar formula, and they tell you how many atoms or molecules are reacting. All right. Another kind of conceptual question. What are things that will affect reaction rate? So how can I affect how quickly a chemical reaction occurs? There are multiple factors that you can manipulate. Probably one of the most important, again, is temperature. Okay? This is one that we use as chemists, as scientists, to increase the speed of a reaction or to slow it down, is we do change the temperature. All right? The temperature can affect whether it goes fast or slow. There are certain ones that like a low temperature, so if I heat it up, it slows down. It doesn't happen as quickly. All right? But other factors would be surface area, concentration, pressure if it's gases, catalyst, you probably learned that back in bio, catalyst or enzymes, okay? A catalyst will help speed up a reaction. And then, of course, it might just be basically the chemical properties of that particular substance. That's what we mean by nature, would be what are the chemical properties. So again, if you have an alkali metal, it's something that'll go very, very quickly. All right. this is kind of a side note, I feel, but it's one that we got to point out. We have diatomic molecules, okay? Diatomic molecules. So, these are 7 elements that will never, ever appear alone. There are 7 elements on the periodic table that if we mention them, if I say, you can see some of them over there, oxygen, you will never find a lone oxygen atom. You won't find just O all by itself. What we mean by diatomic is O will always be O2. Oxygen will always be O2. You will never find oxygen alone. It could be one with another element. Okay? This oxygen's not alone anymore. It's bonded with magnesium. I'm saying you will never see in a chemical reaction N plus O forms bleh. Okay? That's not possible. N cannot be by itself. It'll have to be N2. O cannot be by itself. It'll have to be O2. Okay? And then it'll react and form something together possibly. So these are 7 elements you need to memorize. Okay? I think some people say Brinkelhoff. I don't know whether that's one kind of acronym if you want to try to remember that. All right? There's different ones out there. I don't get big into acronyms too much. If I do a periodic table, okay, one of the ways that I look at this is I got NOFClBri, is I mentioned to everybody that there are 7 diatomics that start at number 7. Number 7 is nitrogen. They then make a 7 on the periodic table, going over, and they stop at the halogens, they stop at the noble gases, but they make the shape of a 7 in the periodic table. So NOF, and then down the halogen line. Now, where this kind of thing breaks apart, I have to go in hydrogen. Okay? But you have 7 diatomics starting at number 7, nitrogen, making a 7 down the halogens, and hydrogen. Okay? Those elements will always be diatomic. They will be the element symbol and then 2 of them. All right, last part for this video at least. We want to be able to, we're not getting into balancing on this video, but I want you to be able to recognize what type of chemical reaction you have. And there are 5 types of chemical reactions. This is a part that I think a lot of people like because, again, it's all about patterns. But this will be very important in our last part of this unit where you have to predict products. You need to identify the type of reaction, and that'll help you figure out how to create the products. Okay? So the first one is a synthesis reaction. A synthesis means to combine, to create. All right? That's where you're putting 2 lone elements together, and they're going to create a single compound of the combination of the 2 of them. So you're going to see we like to do this kind of A plus B forms AB. So hydrogen was A, oxygen was B, and they're forming AB, now chemically bonded together as a compound. So when you have 2 lone elements and they become 1, that is a synthesis reaction. You could technically have a compound and then another element, and then it just forms a larger compound. That would be synthesis as well. Okay, so when you have 2 reactants but only one product, that is a synthesis, definitely. The opposite of synthesis is decomposition. Decomposition is where you start with the compound on the reactant side and then it splits apart. Okay, it splits apart into its elements. Okay, now this one's a little tough where you can see it actually splits into a compound and something else. But the idea would be if you have a single compound on the reactant side and it splits into 2 pieces, it clearly has decomposed. It has broken apart. Single replacement. All right, for a single replacement reaction, this is where we're going to see one element come into a compound, kick one of the elements out, and replace it. So we have one element, single, replacing another one, okay? I used to all the time do like demonstrations with people. This would be where like you have a couple and you have a lone person and the person comes in and kicks one of the people out of the couple and takes the other one. It would be like somebody taking a girlfriend, somebody taking a boyfriend, etc. from a couple, okay? Now, one of the key rules here is cation ions only trade places with other cation ions. So if it's a metal by itself, it will replace the metal in the compound. If it's a nonmetal, it will replace the nonmetal. So you do have to pay attention to what that lone element is. Usually it's a metal, but we do have some nonmetals that do it, usually halogens. So, but you got to make sure you replace the correct one. We do not combine metal-metal, okay, in these reactions. Almost all of these reactions, I will say, guys, will be ionic compounds. Okay, there will be some exceptions, but most of these will be ionic compounds. So here's your form. A plus BC produces, you can see A comes in, kicks B out, and forms AC plus B. All right? So if this is written the way it is, if this is an ionic compound, this A must be a metal because it's replacing the first element, which would be a metal, and then obviously combining with the nonmetal. So you can see here, metal coming in, replacing, well, of course we have a great example here where we don't have a metal, but this would be the cation. So that's fine. Cation replaces cation, and then obviously kicks the other cation out. That's a tough example there. All right, double replacement. This is where both compounds trade partners. Okay, so two couples go to a dance and they go, you know what, I don't like my date, let's switch. Okay, so that's what we got going on there. Double replacement. All right, so cations again still only replace cations, metals, metals, nonmetals, nonmetals. So pay attention to what you do with it. Again, I focus on the fact that only like you just look at the two elements going back and forth. B and D kind of just sit there, and A and C are the ones that are double replacing. Two elements are changing. Okay, so a double replacement reaction here. All right, you can see that the Ca and the Na are switching. So Ca comes in, kicks the Na out, and the Na joins the Cl. And so they have switched on the other side. Ca is now with SO4, Na is with Cl. Okay, so this will happen a lot in neutralization reactions. We'll talk about those a lot later with acids and bases. And obviously this happens a lot of times when you get precipitates, those solids forming from solutions. So there's kind of the drawing of it, or model of it. And then one more, the combustion. This is the only one that, like, it's very specific, okay? You're going to have the same elements always involved in this reaction. So this one, in my opinion, you should be able to identify very, very, very quickly, okay? Because, again, it has the exact same products every single time, okay? So a combustion is what we have. We have a hydrocarbon, exactly as it sounds. A hydrocarbon is a compound with carbon and hydrogen. It can have oxygen as well, all right? But it will react with oxygen, O2, and always form water and carbon dioxide. So these are the easiest to predict the products for. You know it's going to form water and carbon dioxide every single time. I think some people think it's a double replacement or think it's a single replacement. I don't know why, but please be very careful with that. It always forms water and carbon dioxide. These reactions, in terms of properties, they produce a lot of heat. Burning of fuel is an example. So here's your general form. You have some hydrocarbon, so some CH compound. Okay, the X and Y just represent any subscripts that are going to go with it. We always have oxygen on the reactant side, and the products are always CO2 and H2O. And that is your combustion reaction every single time, okay? If you see CH at the beginning, if you see CO2 and H2O at the end, it is always combustion, combustion, combustion. And that's it. So make sure you understand that you understand the signs of a chemical reaction, a chemical change versus a physical change. that you understand the parts of a chemical equation. We're going to really hammer that over the next video as we start balancing, and that you start practicing recognizing the type of reactions that occur, which we'll continue to do that in our balancing, but will come in big when we do predicting products. All right, thank you very much.